Doppler ultrasonography uses two main principles. First, high-frequency sound waves, known as ultrasound technology, penetrate superficial soft tissue but bounce off interior soft tissue like organs. Similar to X-ray imagery, the returning waves can be reconstructed into images. However, unlike with X-ray, the participant is not exposed to ionizing radiation, live imaging can be performed, and ultrasound devices are far cheaper than X-ray devices. The second principle used is the Doppler effect. Most people are familiar with the phenomenon of the sound of a car getting higher pitched as it moves towards the listener and then lower pitched as it moves away. This is due to the sound waves compressing, shortening the wavelength and increasing the pitch as the object moves towards the observer, then stretching out, increasing the wavelength and decreasing the pitch. The same physics apply for Doppler ultrasonography. In this case, the probe is the listener on the side of the road and the blood is the car. While this may seem strange at first due to the probe being the source of the sound and not the blood, what is important is the wave after it is reflected. When the sound wave is emitted, it penetrates the skin, skull, and blood vessel, but bounces off the flowing blood. Because the blood is flowing, i.e. moving toward or away from the probe, it either compresses or stretches the wavelength of the sound wave as it reflects off of it, just as the sound compresses as the car moves closer or stretches as it moves away from the listener, or in our case, the probe recording the information. The probe then sends this information to the computer and its velocity is calculated. Rather than an image of an organ being reconstructed, a visual representation of the blood's velocity and direction can be reconstructed and measured in real time.